Okay, Teddy, so we learned about some of the different things you can see through the quantum kaleidoscope. In this video, we want to explain the quantum kaleidoscope in terms of quantum science. Okay?
Okay.
All right. So the first thing to understand is, what does the word quantum mean? Do you know what the word quantum means?
It means like something that you can count.
Something you can count. So for example, I have here a glass of
Rice.
And if I said count the rice, what would you think I would mean by that?
Just taking out each individual rice and counting them.
Right, so each individual grain of rice.
Yeah.
Yeah, so there's something there to count, which is the grains of rice. And how many grains of rice do you think are here?
A lot.
A lot of grains. It would take a while to count all of them. But the important thing is not whether we can count all of them or whether we can accurately count all of them. It's whether there's something there to count. And with the rice, there's something there to count. Okay?
Okay.
All right, now here's something else. Here's a glass of what? What's that?
Sugar.
Sugar. If I said count the sugar, what do I mean?
You would mean count each grain of sugar.
Each grain of sugar, right? So there's something there to count. So the thing that you count is a quantum, right? Or the things you count are quanta. It's a strange word because there's one quantum and two quanta and three quanta. It's kind of like mouse, one mouse, two mice, three mice. It's a weird plural. So the things you're counting are the quanta, all right? Now, here's another one. What about this? What do I have in there? Flour. Is there something there to count?
Yes.
Could you count it?
No, not really.
No, but there is something there to count, right? So when we look at different things, the question is there something there to count? Now, here's a trickier one. What do I have here?
Water.
Water. If I say count the water, what do you think I mean by that?
I mean, I guess you could count each individual molecule of water.
Right, so you've been told that like water is made up of some tiny little pieces that you can count called molecules. But it's not obvious that they're there. You've never seen a molecule, have you?
No, I haven't.
So it's kind of hidden, all right? So all those are things that you could in principle count, but sometimes it's kind of hidden, and it looks kind of continuous, like it flows, and you might not know there are pieces to count. So there are quanta for each of these things, but none of those quanta are the quanta in quantum science, all right? The place that quantum science begins is with light. So have you gone out into the sunlight and felt that sunlight warm you up?
Yes, I have.
Yes, you have. And what's going on there is the energy from the sun is traveling through space. That light is traveling through space, and it reaches Earth, and it hits you, and it warms you up. Now, if I said to you, count the light, is there anything there to count?
Photons.
Photons, right? So it turns out that there are individual little pieces of light, which, can you see them?
Nope.
Nope. Nobody knew they were there. For thousands of years, people have been walking out in the sunlight and feeling the sunlight, but they didn't know there was anything there to count. But the beginning of quantum science is understanding that light has quanta. There are pieces of light, which, as you said, are called photons. Do you know how many pieces of light, how many quanta of light hit you every second when you're out in the sun?
Billions?
Billions? It turns out it's about 1 billion trillion. It's a huge number hitting you every second, right? But you don't feel that. You just feel the light warming you up, right? So when I tell you there's 1 billion trillion of something hitting you every second, do you have a picture in your mind of what that looks like?
A bunch of tiny things hitting me.
A bunch of tiny things hitting you. So here is a way of picturing what's going on. So I have here another glass. It's my glass filled with light. Now, do you know something about light? That light is made up of many different colors. There are many different colors of light.
Yes.
Yeah. And so even white light, which is hitting us, right, has lots of different colors inside it that you can break light up. Have you ever seen light broken up into its colors?
Yes, like in a rainbow.
Like in a rainbow. Or if you've ever had like a prism like this or something, some cut glass, you can look in there and you can see colors, see rainbows in there. So light is made up of lots of different colors, and you can see the individual colors. And so here is my little glass full of light quanta. Now, I don't have every single color in there. I just have some colors. So what colors do I have here?
You have yellow, red, blue.
Yeah, those are the colors I have in here. Yellow, red, and blue. And so these are my representation of different light quanta. Now, what do you notice about the red, yellow, and blue quanta?
Well, the red one is the smallest.
Smallest.
The yellow one is medium-sized. and the blue one is the biggest.
And what that's supposed to represent is the fact that blue quanta are bigger than yellow quanta, and yellow quanta are bigger than red quanta in terms of the amount of energy that they hit you with. So when you get hit with a red quantum of light, a little bit of energy gets deposited on your skin. And when you get hit with a blue quantum of light, more energy gets deposited on your skin. So these quanta all come in different sizes, okay? And it goes in rainbow order. So the red end of things are the smallest quanta, and the blue end of things and the violet end of things are the biggest quanta. Now, do you know that there's light that you can't see? Light, if you keep going beyond violet light, there's another type of light.
Ultraviolet and infrared and X-rays.
X-rays, right? There's other types of light. So here is my UV quanta. You can't see this, but if you go into the sunlight, there are also quanta of light that are of this type, and they can hit you too. And that's very important for us because these, since they're bigger than like the blue or the other visible quanta, they can do the most damage to you. So this is the reason why when we go to the beach in the summer, you put what on your skin?
Sunscreen.
Sunscreen to protect you from these large quanta, which can do damage to your skin. The visible ones don't really do much damage to your skin. It's these ones you have to worry about. All right? So the fact that there are these larger and smaller quanta explains some things that you experience, like getting sunburned, right? These guys are the ones that are giving you a sunburn. Okay. So now that we have these different quanta, when you think about what light is doing, right, you have this sort of stream of all these different colors in light coming towards your eye and hitting it, right? All the different combinations of colors. And let's just look at one quanta here. Now, the key thing about thinking about these quanta traveling through space is they don't travel like this towards your eye, right? They travel like this towards your eye with the edge on. Okay, Teddy, explain that a photon can travel towards your eye, but in lots of different orientations with its edge forward, right? Can you show all the different orientations it can go in? This way, this way, this way, right? All these possible different orientations. So when you think about all these quanta of light of different colors traveling towards your eye, right? You want to think about the edge going towards your eye, right? In some orientation. And this is called the polarization of the photon. Can you say that word?
Polarization of the photon.
Very good. Okay. So now we understand that light is made up of these quanta, and each quanta comes in different sizes, and each one has an orientation to it, known as its polarization. Okay?
Okay.
Now we can start to understand what's going on with the quantum kaleidoscope. So one layer of the quantum kaleidoscope has this little rectangle in it, right? And what's the picture of what the rectangle looks like? You want to show them?
It looks like this. Well, it doesn't actually look like this, but this is basically what it is.
All right. So what we have here is this rectangle, and it's got a bunch of lines going one way. All right. Now, what happens when you take a quanta going edge on towards this? Can you show people?
Well, if it's going this way, it wouldn't get through. If it's going this way, it would get through. If it was going this way, half the time it would get through, and half the time it would turn in and it wouldn't get through.
All right. If you have light going horizontally, aligned with this, it's going to get through 100% of the time. If you have light going vertically, perpendicular to this, it gets through 0% of the time. And if it's going diagonally, half the time it gets through and rotates, and half the time it doesn't get through and actually rotates the other way.
And that's why it's kind of tinted. Half the time the light gets through and half the time it doesn't.
Okay, yeah, because we think about it, the light coming in comes in all different orientations. Random orientation. This is called randomly polarized light or unpolarized light. Anything going this way makes it through definitely. Going this way doesn't make it through definitely. But other orientations, sometimes it makes it through, sometimes it doesn't. The rectangle in the kaleidoscope, which is called a polarizer, only lets some light through. Now it's called a polarizer because all the light that gets through, right, is all going in the same orientation. It has the same polarization. Right? So once light gets through, it's one of these is always going that way, or whatever orientation this is in, right? If this is this way, then these photons are going to get through. If it's this way, then these photons are going to get through. Okay?
Okay.
All right. So now that we understand about how this polarizer works, how one layer of the kaleidoscope works, we understand that only about half the light gets through. Let's think about two layers, just looking at regular light. So can you explain what happens if you have two layers and they're lined up with each other, what you see and why you see it now that you have this model in your mind?
As we know, the first one, half the light gets through. If you put it like this, all the light is already in the same orientation, so still half of the light gets through.
Right, so everything that got through the first layer is already oriented to make it through the second layer. So the second layer doesn't absorb any light, right?
Right.
So now what happens if you rotate that, let's say 90 degrees? So it's perpendicular. What do you see in the middle there?
It's black.
It's black, and why is it black?
Well, because half the light that goes here is now oriented in this way. Then, once it gets through, it's all oriented this way, so this layer, the back layer, blocks it.
So the light that makes it to one layer is oriented exactly perpendicular to the polarizer in the second layer, so the polarizer in the second layer blocks all the light. So now what happens if one of the layers is diagonal to the other one?
Well, the center in the diamond is darker gray because once it gets through here, half of the light gets through here, and the half of the light that gets through here is all vertical.
Vertical, because the first layer is vertical.
Yeah. And then, since it's vertical, half of the light turns and gets through the back layer, and half of it turns the other way and doesn't get through the back layer.
Okay, so the vertical light, when it gets to the next layer, half the time it's going to go through, and half the time it's going to get blocked.
Yeah.
So you see half the light gets through the first layer, and then only half of that gets to the second layer. So how much light gets through both layers?
A quarter of the light.
Quarter. So it's not as much as gets through just one layer. So that's why it looks darker, but it isn't completely black.
Yeah.
Okay. So now let's look at three layers. Let's have two of the layers be perpendicular and one of the layers be diagonal. And tell us what you see and then explain what you see.
Well, now there's a black square in the center because if any two layers are perpendicular to each other, then it makes a black square because they're already oriented in one direction.
Right, so if you have any two layers in a row that are perpendicular to each other, the photons that make it through one layer are going to be blocked by the next one.
Yeah.
Okay, so you'll always see the black square, except what happens if you put that diagonal layer between the two layers that are perpendicular?
Well, now there's no longer a black square in the middle because once it gets through the first layer, half of it that gets through is all now pointed this way. Then, since the second layer is diagonal, half of the light that's going this way gets through that way. And then, same for the third layer, half of that light gets through that way.
Okay, so half the light makes it through the first layer, and then half of that makes it through the second layer, and then half of that makes it through the third layer. So a half of a half of a half, which is, do you know what that is?
An eighth.
1/8. So an eighth of the light still makes it through when you have that particular orientation, unlike the case when you just have two that are perpendicular right in a row, and then no light makes it through. So by adding that extra diagonal layer between the perpendicular layers, more light has gotten through than if we just had the two perpendicular layers, right?
Yeah.
Which is kind of surprising because every layer of the quantum kaleidoscope will only absorb light, right? It will never give you more light. But somehow if you add in an extra layer, you get more light through in total. Why? Because of the photon polarization.
It helps it rotate the way it needs to go so you can see it.
Exactly. And now we understand about quanta and how the science of these quanta explains the effects you see when you look through the quantum kaleidoscope at regular light. So now let me talk about some terms that come up in quantum mechanics and explain what they mean. So the orientation of the photon is known as the quantum state of the photon. Like state, if you said, are you awake or are you asleep? What state are you in?
I'm awake.
You're awake right now. And this photon is horizontal, this is vertical, this is diagonal. These are all different quantum states. Now, Teddy, how many different quantum states are there?
Infinite.
Infinite. There are infinitely many quantum states. When you send a quantum state through the polarizer and look at it, right, you have made what's called a quantum measurement. We've measured which way it is. Now, there's only two answers to the question, does it make it through or does it get absorbed, right? Either it makes it through and it's going this way, or it gets absorbed. So when we make a measurement of this quantum state, we only get one of two answers. And this is called a binary question. So if I ask you a yes or no question, right, there's only two answers, yes or no. When we use this polarizer in the quantum kaleidoscope, and we're asking, does the photon make it through? Either yes or no. So this is called one bit of information. It's the smallest amount of information we can have, yes or no, on or off, it makes it through or doesn't make it through. Two possible choices. There are infinitely many different quantum states, but when we make a quantum measurement, we only get one bit of information. And that means that this is what's called a quantum bit. Infinitely many states, but only gives us one bit of information. And another name for a quantum bit is a qubit. Quantum bit, qubit. You put the two words together and get qubit. Now, another term that comes up is you have light going this way, vertical, and you have light going this way, horizontal, right? And you have light which is going diagonal, which is not horizontal or vertical. And we will say that light which is going diagonal is a superposition of light going horizontal and light going vertical, meaning it's a kind of combination of light going vertical and horizontal. Does it make sense that diagonal is kind of partly vertical and partly horizontal?
Yeah.
So diagonal light, you can say, is a superposition of horizontal and vertical. Can you say that word, superposition?
Superposition.
Is that a fun word to say?
Kind of.
Kind of. But you could also say that vertical light is a kind of combination of diagonal one way and diagonal the other way. Vertical light is a superposition of diagonal one way and diagonal the other way. Horizontal light is a superposition of diagonal one way and diagonal the other way. So everything you can view as a superposition of other things. But when you're making a quantum measurement, this kind of determines a particular orientation. And so you would say, light which goes through straight this way, well, that's horizontal, that matches the polarizer, definitely makes it through. Vertical light definitely gets absorbed. And light like this, well, is it going to get absorbed or not? Well, it's in a superposition of the absorbing light and the light that makes it through. So this kind of determines whether we consider something to be in a superposition or not.
Okay.
Okay. So now there's some understanding about why you see what you see when you look at just regular light, look at things around the room. But we also saw there were interesting things that you could observe when you looked at screens. So do you remember looking at a TV screen with one layer of the quantum kaleidoscope, what you saw?
Yeah, I think it looked so clear when it was vertical, grayish when it was diagonal, and black when it was horizontal.
So now, can you explain why it looks black when the kaleidoscope layer is horizontal and you're looking at a TV screen?
Well, that is because most TV screens, all of the photons that they emit are all oriented vertically.
Vertically. And so that means with one layer, you can block all the light from a TV screen,
Yeah.
right? Or let it all through if it was vertical. And it looks just like a piece of glass, right?
Yeah.
Okay. So now we understand that. Now, when you looked at a computer screen, right, we saw different colors for different orientations.
Yeah.
Can you explain why we see different colors through just one layer as you rotate the kaleidoscope layer?
The reason is because, well, most of the light is going through this way, but it happens to be that some blue light and some red light is going this way. And that's why it looks purple when the kaleidoscope is horizontal.
And when it rotates vertically, because there's a little bit more green light going through vertically, it looks a little green.
Yeah.
Because each color has its own photon and they can be oriented different ways, you can make screens which typically emit 3 different colors of light. Each color light can have different photon orientations, which means you'll see different colors as you rotate the polarizer layer of the quantum kaleidoscope. So now, let's look at this cool effect we saw with 2 layers when we looked at a screen. Right? So you looked at 2 layers, one of which is, let's say, horizontal, and the other one is diagonal to it. All right.
Yeah.
So in the orientation you have it in now, what do you see in that central diamond?
Right now, in the central diamond, it's purple.
Purple. Can you explain why it's purple?
Well, because since it's horizontal, the light that's getting through makes purple light.
Right. The first layer is horizontal, so we get that purple layer, yeah?
Yeah.
And then
And then all those blue and red photons can half of the time get tilted this way.
Okay. So some of those can make it to the next layer.
Yeah.
All right. Now what happens if we reverse the order? We rotate that 45 degrees. So the first layer is diagonal and the second one is horizontal.
Now, the reason I don't see the purple where they overlap, the reason is because half of the light that's getting through, which is a combination of all the lights that makes white light, gets through, and now it's all oriented diagonally. Then, half of that light gets through the next layer where they overlap, so then it's
A little bit darker, but all the colors got through.
yeah.
So it doesn't look colorful anymore. And all I have to do is flip it, and we see the purple again. So it really matters what order the kaleidoscope is in and the orientation of the light coming in. So now we can explain this effect using the kaleidoscope. And then we can add in more and more layers and all these different combinations. But all the different combinations you see in all the different patterns, you can explain if you just understand about light quanta, right? Photons, their quantum state, their orientation, and the measurement with the polarizing layer and what happens there. Make sense?
Yeah.
Okay, great.